How's everyone doing today? Fair enough. Alright. Brief reminders of a few things. Today's Monday the 24th. The Chapter 5 homework and quiz are technically due on the 26th, since we didn't have class on Friday to talk about it. So if you have any questions about that, we can spend as much time as you want looking over those assignments. Main thing for this week is going to be Chapter 6, which is about momentum and collision. We're still going to be tying kinetic energy back into it. We won't be done with energy really at all this semester. And I want to at least go through the definition and formula for momentum today, no matter how much homework questions you guys have. I want to at least make sure to start Chapter 6 today, because we do have lab this week, and then we'll be about momentum and collisions, and tying it back to kinetic energy. Do you agree? So, does anyone need anything? Any questions, comments, or yes? 9. Yes. Find myself which one that is. All right. Homework question number 9. We have a car driving at constant speed down the highway. Most of the power developed by the engine is used to compensate for mechanical energy loss due to frictional forces. So this is similar to most normal cars and vehicles in general. When you're moving forward at constant speed, the engine has to be constantly exerting force forwards to counteract the forces from friction that point backwards. The only way to maintain constant speed is if all the forces balance out. So the force from the engine has to equal and cancel out all the forces trying to slow you down. So the power developed by the engine is 159 horsepower. Estimate the total frictional force acting on the car when it is moving at a speed of 24 meters per second. 1 horsepower equals 746 watts. They've rounded it up for us. So, we've been given the car's power, the power rating of the engine. So P equals, insert sample number here, I've got 159. That is in horsepowers. We are going to have to do something about that. And we're being asked to find the force of friction being exerted on the car as the car drives at some constant velocity. Your number will vary. Mine is 24 meters per second, which is pretty fast. So, we have power, we have velocity, and we need a force. What formula singular comes to mind at this point? Correct. One of the power formulas, we did look at 2, just to review briefly. The definition of power is work over time, but there's a secondary formula. Power equals force times velocity. Now, technically speaking, if you plugged in the power output of the engine and the velocity that the engine is making the car move at, this force would be the force the engine exerts. However, we're told here we're moving at constant speed. Most of the power developed by the engine is used to compensate for the mechanical energy loss due to frictional forces on the car. All of that force that the engine's creating, the F that formula will tell you, exists to counteract the frictional forces. So even though we're technically solving for force of the engine, to be moving at constant velocity, the force of the engine would be equal to the force of friction slowing us down. F engine here is equal and opposite to F friction. So if we use this formula to define force of the engine, that should still give us the answer. We have power, we have velocity, we have force. It's almost as simple as just utilizing the formula. The main catch is your power is given to you in horsepowers. You do have to convert it to watts first. HP. We're told 1 HP is equal to 746 watts. That will be the same for everyone. And you will get a lot of watts. Whatever value you get there, plug it into P equals FV, excuse me. No, is my calculator at my house? No, it's not. Thank goodness. A lot of watts. And once you have power in watts, power equals force times velocity. Solve for force. Just to prove that this does work, I will get the answer from my sample numbers. F equals 4,942.3 approximately, which is within rounding range of what the sign is expecting when you factor in sig figs. How's this one feel? Okay. What else? Anything on your minds? Any other questions? Time feels all right then, I hope. Excuse me. All right. Well, any other questions pop in your minds, do please let me know. And we can also still talk about this on Wednesday, because it is due Wednesday at midnight. Additionally, as a reminder to advertise tutors, there's tutoring on Tuesdays and Thursdays, so if you're not quite done by tomorrow night, you can also come in here and get some help from some people who know what they're doing. So, there's nothing presently on your minds. Let's begin looking at chapter 6. Chapter 5 was about energy, and energy as a concept is present in every aspect of our lives, but again, it's also hard to define because you can't really observe energy itself. You just know that something has energy because you can see it doing things with that energy, or it has that energy stored to be able to do things later. Momentum, the concept of momentum, is similar, but is different in a few key ways. You guys, has anyone in this room not heard the word momentum before? Okay, just checking. Now, when you hear the word momentum, just based on how you might have used it in the past, or based on how it's used in common speech, what sorts of meanings does the word momentum conjure? How is it commonly used as a word? Say it it again?
Gaining and losing momentum.
All right, so momentum is kind of like energy, something that you can build or lose. And you tend to hear about building momentum as this idea of acquiring something that makes it easier to keep moving. Like a team builds up momentum and they're able to accomplish more things because they're already working and moving. Or when you lose momentum, suddenly everything comes to a complete stop. That image from that word and how it's commonly used is actually pretty accurate, unlike how common English uses a lot of science words. I'm going to summarize all these words, don't worry. The idea of momentum is it's something very similar to kinetic energy. Kinetic energy is a form of energy that when you have it, it makes you start moving. And the more kinetic energy you have, the faster you will move. When an object that has kinetic energy strikes some other object, there's going to be an energy exchange involved as the kinetic energy turns to a different state, moves to a different object, etc., etc. Momentum is very similar in a lot of those ways. The idea of momentum, the official textbook definition, momentum is a quantity related to the motion of an object with matter. An object needs to have both mass and velocity in order to have momentum. The formula for momentum shares a lot of things in common with the formula for kinetic energy. Both have some mass term multiplied by some velocity term. To have either momentum or kinetic energy, you need to have mass and you must be moving. So that is something that is still in common between the both of them. Here's where the differences start piling up though. Velocity is a vector and mass isn't. In the kinetic energy formula, since the velocity term is squared, vector times a vector, that kind of causes the vector hood to close in on itself and cancel out. So kinetic energy is not a vector. Energy doesn't care what direction it's moving in. It just wants to keep moving, like a small child who ate a lot of candy. Momentum is slightly different because looking at this formula, the P stands for momentum. I'll explain that better later. Momentum equals mass times velocity. Mass is still a scalar, velocity is still a vector, but it's not squared this time in this formula. As a result, the vector hood doesn't cancel out, and momentum is still a vector. Whatever direction your velocity has, momentum inherits that direction as a part of this formula. So if I'm moving east, I'll have momentum directing me to keep moving east. One of two key differences between momentum and kinetic energy is that momentum is a vector and kinetic energy is not. Say I fire a cannonball at a brick wall. What we're going to have here is a collision, one object striking another. And in that collision, there's going to be an exchange of energy and momentum between everything involved in the crash. When the ball hits the wall, the ball is going to lose kinetic energy because that energy is going to transform into different forms and enter different objects. And as you could probably imagine, it's going to blast through the wall and probably throw bricks everywhere. So kinetic energy will end up in the bricks, among other places. Cannonball will have less energy. Thing is, though, the energy of the cannonball doesn't care what direction the ball or the bricks end up moving in. All energy cares about is that everything is moving all the time. So if energy was the only thing to be concerned with, you could get a scenario where the cannonball just made of wrought iron might bounce backwards off of the wall because the energy doesn't care about the direction. But momentum does. Whereas energy is the reason that everything bounces away all chaotically, momentum is the reason that the cannonball will actually bother to blast through the wall in the same direction. Cannonball has rightward pointing momentum, so it wants to keep moving to the right until something stops it. The wall's going to try, but odds are it'll fail, so it's funnier that way. And because the cannonball has rightward facing momentum, that's what's going to keep carrying it in the same direction, whereas energy doesn't care. So as we start defining and using momentum, one of two main things to keep in mind about it that make it different from kinetic energy is that it is still a vector, like the velocity used to calculate it. And it's the reason that things it's what determines the direction that things move in a collision, whereas energy itself doesn't care. Questions so far? All right. So, the formula for momentum is rho equals mass times velocity. That p up there is technically not a lowercase English p, it is technically a lowercase Greek rho. I was not the one to make that decision. It's basically just a lowercase English p. However, uppercase p is reserved for power, and lowercase p is, well, honestly, lowercase rho is just a small uppercase p. So that's even more confusing. It's not going to matter very much, but if it comes up, most computers will put this little extra hat on top of a lowercase p, whereas rho is smooth all the way around. And uppercase p, I think academically speaking, is flat on this side, literally like a D with a tail. Rho is round all the way around. So it's more like a circle with a tail than a D with a tail. It's not a big difference, but it is technically rho, and I'm supposed to teach you that. Since it's rho, I'm occasionally just going to say rho equals mv, and sometimes I might call it rho momentum, if that helps you remember. I don't know the real reason why we use that, but there's this dumb old story about how momentum used to be called pimentum because of a dumb reason involving a pimento. That's the only reason that I've ever been given for why it's rho instead of something else. But technically M is already reserved, so that's got to be one reason why. I'm rambling at this point, sorry. Rho equals mass times velocity. What this formula tells us is the faster something is moving, the more momentum it has. Momentum can be thought of as how hard it is to stop a moving object. An object moving very quickly to the right wants to keep moving to the right. And it's going to keep doing that until something stops it. The more momentum it has, the physically harder it is to stop. And you can increase momentum by either increasing velocity, the faster you are, the harder you are to stop, or you can increase the object's mass, because the bigger the object is, the more momentum it has, the also harder it is to stop. What was I saying? Imagine you walking at 1 meter per second, that's a fairly common walking speed, next to a train, a full-on freight engine, that's also just chugging forwards at 1 meter per second. You both have the same velocity, but the human has way less mass than the train. And so even though the train's moving pretty slowly, do you think you'd be able to grab onto it to stop it? No, a train has a lot of momentum because of how much mass it has. Even though it's moving slowly, it is very hard to stop it, and that's why trains sometimes need like miles of dead track in order to actually come to a complete stop. So again, I'd say the main definition to really remember when it comes to momentum, it's a metric for how hard something is to stop. And if you've already stopped, then it's pretty easy to keep you stopped because you're already there. So when velocity is 0, momentum is 0. I've been comparing momentum to kinetic energy, but now I need to compare it to something else. That's what makes momentum also different to the concept of inertia. We don't really use inertia that much in here, but we did describe it when talking about Newton's first law, since that's the law of inertia. The law that says an object at rest remains at rest and an object in motion remains in motion until acted upon by an outside force. Momentum is again similar. An object with momentum wants to keep moving in a straight line forever, like how inertia tells us objects like to do. The main difference between momentum and inertia is inertia is still true even when you're not moving. When you're stationary, you have inertia telling you to remain stationary. But since the formula for momentum is mass times velocity, if you have no velocity, you have no momentum, even though you still have inertia. The inertia is telling these markers remain still, whereas they have 0 momentum, and therefore momentum can't tell them to do anything. So momentum is similar to both inertia and kinetic energy, and yet it's still somehow different to both. Last detail about momentum before we actually use the formula and some quick math. It doesn't really have its own dedicated unit. Kinetic energy is measured in joules. Inertia is measured in grams. Momentum, its unit is just the 2 units multiplied together to make it. It's just kilograms times meters per second, which comes straight from the formula. Multiply kilograms times meters per second. No one ever decided to give it a more specialized unit. On the one hand, it means there's fewer units to memorize. On the other hand, kilogram meters per second is a bit of a mouthful. I get the feeling that, I know Newton got credited with force and gravity, but Newton's the one that wrote down momentum, and then all of Europe started using what he wrote about momentum as well. So Newton also got famous for momentum. Obviously, he wasn't the first person to notice it, but he's the one who got famous for writing it down. Arguably, his work on momentum is probably as important as his work on force and gravity. And yet, for some reason, his name was already used up for the unit for force, and so they didn't have any name to put on that. I'm just rambling. I apologize. Any questions before we do math? All right. So, there are 4 objects, entities, including the dog, that all have some amount of momentum. I'd like you to tell me which one has the most momentum. 1, a stationary building with a mass of 100,000 kilograms. 2, a 10-gram bullet fired at 1,000 meters per second. C, a 25 kilogram dog running at 10 meters per second, and D, a 2,000 kilogram car driving at 1 centimeter per second. Which of these examples contains the most momentum? Ergo, which of these objects is the hardest to stop? So, A, B, C, or D, which one do you think has the most momentum?
Do you not have to convert the 10 grams?
You would. I wrote it up there the way it is as a trick. You were correct. So for looking at B, 10 grams fired at 1,000 meters per second. As I said, the unit for mass we want to use for everything is kilograms. The unit for momentum should be proof for that. 10 grams converted to kilograms is 0.01. Therefore, subject B has 10 kilogram meters per second of momentum. How much does A have? None. It's not moving. Doesn't matter how massive a building is. If it's not moving, it's very easy to stop because it already is. How about the dog? 250. And the car. What's the thing you got to notice about this one? Yep. So 1 centimeter per second is 0.01 meters per second. So that's only 20 kilogram meters per second. So the dog wins, despite not being the fastest or the most massive. I'd say that the dog's momentum there is equivalent to or even less than like football players getting tackled by each other. So yeah, that much momentum can knock a person down. How does this feel so far? I know the formula itself doesn't have that many tricks to it. It's just two things multiplied together. All right. So, momentum is a vector, measures how hard something is to stop while it's specifically in motion at a specific speed. And it is similar to kinetic energy, but not identical. To continue comparing it to kinetic energy for a second, I mentioned earlier the example of cannonball hitting a wall And in that interaction, there's going to be an exchange of kinetic energy between the cannonball and the various bricks that make up the wall. In the crash, the cannonball is going to lose kinetic energy. Energy will transfer into the bricks of the wall, so the cannonball slows down, whereas the bricks speed up and blast everywhere. Momentum actually works pretty similarly. An object that's in motion has both simultaneously kinetic energy and momentum at the same time. Again, if you have it. As long as something has both mass and velocity, one object will have both of these at once. So it's not a case of, does it have momentum or does it have KE? They exist simultaneously. One object that is moving has both at once. And we've been talking about what happens to energy when you perform some process. When you do work to transform energy and you have a before state and you compare it to an after state. Again, with this brick wall here, the before state, cannonball is moving at top speed, it has kinetic energy. The after state would be after the cannonball hits the wall and energy transfers from the cannonball into the various bricks of the wall. We're going to do the same thing with momentum, because just like energy transfers out of the cannonball in this crash, and there you have a before state and an after state, the same is true of momentum. When the cannonball hits the wall, momentum is also going to transfer out of the cannonball and into the bricks of the wall, just like how the kinetic energy does. So this momentum exchange is happening at the same time as the energy exchange. What it means is, like how we've been talking about energy, mechanical energy, the total momentum in a system initially, before something happens, usually we refer to it as a collision, because momentum involves moving forwards and things only tend to stop when they hit other objects, so we call those collision questions. Even catching an object in your, like if someone throws a baseball at you and you catch it in a glove, that is, scientifically speaking, a collision. Total momentum initial, before something happens, before a collision, is equal to the total momentum final after the collision takes place. Because like energy, it's the total amount of momentum an object has is going to remain, well, the total momentum in a system remains constant from beginning to end. It's just like the energy does, it's going to transfer between different objects. Using the brick wall again as an example, the cannonball has momentum and it's bringing momentum towards the brick wall, and in the crash, the cannonball loses momentum because it's going to slow down, and the bricks of the wall gain momentum, that's why they go flying. So again, another comparison energy. This will work very similarly, and we're going to utilize that in a brief example now. A 10-gram arrow is fired at 25 meters per second at a wooden log target. A log has a mass of 5 kilograms and is initially immobile. Now what I'm envisioning is just firing the arrow at a stump that's sitting still on a fence post, just target practice. And before the collision, arrow is moving, log is not. So each object has its own different mass and its own different initial velocity. After the collision, arrow is going to stick in the log. But if the log is just balanced on a fence post and you hit it with an arrow, what do you think is going to happen to the log after the arrow lands in it? When you throw a baseball at something sitting on a fence post, what happens to the object after the collision happens? Falls over. The arrow is going to collide with the log, transfer momentum into the log then starts moving, and it's going to fall off the fence post. So, whatever their initial velocities are, they will have some different unknown final velocity after that momentum exchange in the crash. So, to list variables in the corner of the word problem, as I tend to do, we are told mass of the arrow, 10 grams. Initial velocity of the arrow, 25 meters per second. Mass of the log is 5 kilograms. And then the log's initial velocity is 0 meters per second. The two objects are going to stick together and fall off of the fence post at some unknown final velocity. So at the start, that's everything we know and everything we don't know. First question, how much momentum is in the system before the collision occurs? That's the initial side here. Total momentum initial, we need to look at the momentum in each object separately and add them together. Initially, the arrow, we've got mass of the arrow times velocity initial of the arrow, and we'll have mass of the log times velocity initial of the log. Arrow's mass, 10 grams, I need to convert that to kilograms, times its initial velocity. Log, meanwhile, has a mass of 5 grams, but an initial velocity of 0. So in this initial state, it's not contributing any momentum yet. It's not moving yet. All the momentum is in the arrow, like how all the kinetic energy would be in the arrow. So, that means that if we solve for the arrow's initial momentum, that would be 0.25 kilogram meters per second. That is the total momentum in this entire system before the collision happens, as the arrow is just flying through the air. Second question, how much momentum is in the system after the collision ends? Total momentum initial equals total momentum final. That same total amount will remain from start to finish. It's just some of it's going to leave the arrow and enter the log. But like how energy is conserved, momentum is also conserved. If this much energy exists, if that much momentum exists before the collision, this much momentum must exist after the collision. Oh, additionally, momentum's a vector, so it's important to describe what direction things are moving in. So, this is the initial momentum. The final total momentum will be the same value. That means that we already know the final momentum, and that will help us figure out what the final velocity of the two objects stuck together is. Any questions so far? All right. I want to shift this a little bit. I'm going to transition my work into being a continuation of this formula. We've already done the initial side, so now we're going to fill in the final side. On the final side, arrow still has some momentum. That's going to be equal to its mass times its final velocity. Now the log will also have momentum equal to its mass times the final velocity. The log is gaining momentum in this collision so that it's now going to move at a different final speed. The arrow is losing momentum, giving it to the log. So the arrow will slow down, but it will still have some momentum left based on the final velocities. Now, this kind of example is actually one of the easier momentum collisions to work because the two objects are sticking together. Physically, the arrow is going to embed in the log, meaning what does that mean about their final velocities in relationship to one another? They're the same. They're stuck together. They have to have the same final velocity. So rather than having to find two different VFs, in this specific case, it's the same VF. It's one variable, which makes the simplification easier. There's no two equations, two unknowns right now. It's just one unknown in two places. So, mass of the arrow times our unknown VF plus mass of the log times our unknown VF. Whatever these are, they have to add up to the same amount of momentum as the initial side. The same VF, so we can use the distributive property to figure this out. Distribute VF out, that will leave us with 0.01 plus 5 times VF. Divide both sides by 5.01, and that should tell us the final velocity of the combined log arrow system. We've got 0.0499 meters per second, and since it's a vector, this velocity will keep the same direction as the momentum on the left side, so they'll be moving to the right. Very slowly, but they will move to the right. They will budge and possibly fall off, I suppose. Questions thus far? All right. I know it's Monday. I know this is new. Your minds could be anywhere right now, and that's valid. We'll break here for the day. Main things I'll just inform you of is this week's lab does involve this material. Obviously, we'll review it in lab itself. Lab will specifically be about causing different types of collisions on the air tracks that we used last week. We're gonna do two different types of collisions and examine what happens to momentum in the different types of collisions and also kinetic energy in both different types of collisions. So bring these notes to lab. If you have any questions, let me know. If not, I will see you for lab or lecture on Wednesday. Have a good Monday.